All right. Hey guys, what's going on? Today we're going to be talking about solutions to the Klein Gordon equation. So in the last video, we started to sort of dive into quantum field theory. We talked about the Klein Gordon Lagrangian. Now we talked about how sort of that gave birth to the Klein Gordon equations. The Klein Gordon equation came from the Euler-Lagrange equations, which was the attempt to minimize the action of some field, the action being a number that was assigned to some configuration of space, of a scalar space. Okay, so this is what we had so far. We had our Klein Gordon Lagrangian, our Klein Gordon equation, and phi here is some scalar field. Right? So it's a function of space and time. Its derivative is also a function of space and time. And I have points here just to illustrate what we're actually kind of visually what we're dealing with. So here what we're doing is we're saying each one of these in the continuum limit, right? We said that this was in the continuum limit, so every point in space and time, like from here and then here and here and here, like everywhere in space, everywhere in time, there is a point, okay? And that point has, there's a function attributed to that point, okay? We want to know what that function looks like, okay? So in this video, we're going to cover some special relativity, and then we're going to use that special relativity to understand the dynamics of each point in space, okay? Each point is linked to each other by some tiny little spring also, okay? So there are multiple solutions to the Klein Gordon equation, but before we continue with the analysis of this equation, let's review a little bit of relativistic energy. So in special relativity, we have things called 4 vectors and 4 covectors, okay? We kind of talked about this a little bit before. These vectors exist everywhere in space-time, okay? Exist everywhere in space and in time. So let's consider the following product between a 4-momentum vector and a 4-momentum covector. Suppose we have this object here. We're just going to, so momentum times momentum of some light particle, okay? So momentum is mass times velocity, so mass times velocity. So suppose we have something that looks like this. So momentum times momentum is momentum squared, mass squared times velocity squared. All right, so we can lower the index with our Minkowski metric, right? So we can do that. So here's that full-on multiplication, right? Here's we're proposing that our 4 vector looks like this, okay? We're multiplying Minkowski metric, and we do this, right? So as we saw last time, really multiplying by the Minkowski metric changes the sign of the temporal vector. Or the spatial parts of the vector, so we get this, right? Because this 1 times this guy is just going to give us this guy back, this times this times this, and then this times this. So all these guys, this is our Minkowski metric, changed to these signs, okay? And so this then times this is this, and then we get the times this. So that we get this down here, where the p vector is squared, okay? So m squared c squared, then we said, is equal to e squared over c squared minus p squared. So if the particle has 0 momentum, if this thing is 0, well then we get this, okay? Well, we can multiply both sides by c squared, so we get m squared c to the 4th equals e squared, and we get this. So when the momentum is 0, we have recovered Einstein's famous relationship and have shown, and so we can therefore show this thing right here. So as long as our momentum 4 vectors look like this, we can recover Einstein's famous equation, okay? And this is some invariant, some invariant object under transformations. We won't talk about that right now. So, this is special relativity in a nutshell. Not in a nutshell, more special relativity. And it's the relativistic energy sort of side of special relativity. We're calling that equation 2. Let's move on. All right, with this in mind, let's now propose a solution to the Klein Gordon equation that we derived from the Klein Gordon Lagrangian, and we'll see how this works. So this is what we're saying here is that every point in space and time has a function or has a value applied to it. Okay, that value is, we're going to give it some number. Okay, and so we're going to propose that number, its dynamics look like this. Okay, so we can think of these points in space-time as vibrating. Every little point in space has this little vibrating string. Okay. So with this equation, we can take our temporal derivatives and our spatial derivatives. We could say the temporal derivative of our solution of phi. Right. So we put this in here. I realized right now that this was flip-flopped, so this should be omega t minus kx. All right. So we bring with this, so the double derivative with respect to time. So we're really bringing this exponent over, right? So negative I times omega t, right? So when we're taking that derivative, this should be negative, right? Because I have negative right here. And we do that 2 times, right? Because we're taking 2 temporal derivatives. Negative times negative is positive. I times I is going to give us negative 1. So we have this negative in front here. We have omega squared, and then we have this here. All right, let's do the spatial derivative. When we do the spatial derivative, we have negative times negative. That's going to give us a positive, and then do it again. It's going to give us another positive. I times I is negative 1, so we have negative k squared omega, or e to the minus I omega t minus kx. Okay. All right, so placing 5 and 6, so 5 and 6 into our Klein Gordon equation, which was this guy right here. So we calculated our spatial derivative, or our temporal derivative, we calculated our spatial derivative, then we just multiply by m squared. Right, so here's our spatial derivative, will give us our omega, our temporal derivative, and our spatial, and then our multiplication by our mass. And then we set that equal to 0. So omega, so negative omega plus k, because now we divide everything through by this guy here. Okay, so we need the condition then that negative omega squared plus k squared minus m squared equals 0. Multiply everything by negative 1, okay? And then from here to here then, well, this can be thought, k, we're going to define k, mu, as equal to omega, some vector, right? This is some vector, omega, kx, ky, kz. And then when we raise an index, right, k mu is equal to this. Remember, we just changed the sign on all of these. And one's a vector, the other one's a covector. Okay. So when we do that, we get this bit. This bit right here is this right here. And then we take this guy, bring it over to the side. We lose the negative sign when we do that. And so we get this here. This is a dispersion relationship. So this is equation 7, which I've labeled. This is called this dispersion relationship. And this has to hold true for our proposed solution to work. And so lucky for us, the equation 7 looks a lot like equation 2, which is right here. Right? It looks like this because this really is this, where P looks like, I'll say looks like K, or maybe I'll say that the other way around. K looks like P, right? So K looks like P. So this thing then, look at this. This is kind of interesting, right? Because this here is equal to m squared, whereas this thing here is equal to m squared c squared, right? So we just add the c squared here. So we can see that this is clearly momentum. This is kind of like a momentum-ish, momentum squared, but not really because we don't have the c squared. So that's how we say this looks a lot like like equation 2. So we're going to say that this solution is good. And so we say that this solution is good for our relativistic purposes, right? Because this is relativistic energy over here. This is what we're talking about over here. We're talking about relativistic energy and momentum. Again, my apologies for the dog. Yeah, like Great Pyrenees, he's hard to shut up. So notice that we could also have proposed an alternative solution to our Klein Gordon equation, something that looks like this, right? Instead of a minus sign out here. All of this would have worked if we just had no minus sign. And we can look at this, right? So we could say the temporal derivative, the second derivative of the temporal component with respect to the temporal component. We do this all the same way. I squared, again, gives us this minus omega. And just as we got up here, this minus omega bit. And then because we had minus xt, or minus kt, again, that's going to be negative I times negative I, so negative times negative is going to be positive, and then we get these guys again, and so we get that k squared, and so we get the same exact thing if the dispersion relationship also holds for this solution. So we have two solutions now. So we have a solution in which we have a minus sign up here, and a solution in which we have a positive sign up here. And the dispersion relationship holds for both. So so we went through this. Okay, so equation 9 then matches equation 6, right? So equation 6 right here. And so this solution 8, this solution, will also work as a solution for our total solution then. I'm saying solution a lot. But the idea here is that the solution, this here, our number, is this thing here plus this thing, because if one thing is a solution, the other thing is a solution, the idea here is that the combination of the two is also a solution. This term is absent in non-relativistic quantum mechanics because this introduces this weird notion of this positive omega t part. And we'll get into that, but not quite yet. So we're not done yet. These are wave solutions with k and omega being frequencies along their respective directions of propagation, right? So we can think of k as being the frequency along k. What this really is, right? If we really want to go full 3D here, or 4D, it's going to be omega t. Omega t plus, this is just for this one, right? Plus k x times x plus k y times y plus k z times z, right, where each one of these is a frequency in each direction of propagation, and this thing is a frequency in the direction of t, in the direction of time. So each spring has a mass then that is associated with the position and momentum also. So let's revisit this idea of a coupled spring. So what we found is that the position of each point can be described as a sum of complex exponentials. Remember, we're in the continuum limit where every point in space and time is now being described as some combination of complex exponentials. Complex exponentials, if you recall Euler's formula, can also be written as a sinusoidal behavior. So, in other words, the dynamics of each point is kind of fuzzy, right? Because we can, each point is sort of, as we see here, vibrating, right? And we'll see how this is kind of a vibration pattern. It's not quite obvious how this depicts vibrations, but as we continue with this video, we're going to see how exactly the vibration, these are frequencies, really. They're vibrating with certain frequencies, okay? So let's continue. So this here is this here, and each one of these things is vibrating, okay? Each point vibrates in t, x, and y, x, y, and z. And this is what's weird, right? Because vibrating in x, that's kind of that makes sense, right? So that something can be sinusoidal in x. Well, what about in t? Well, as time progresses, these things are vibrating along the temporal dimension. Thinking of that is a little bit weird, right? Because you can have, for example, it's fairly easy to understand x and phi, right? As we travel in x, right? So say I'm traveling from here to here. This is what our solution looks like, okay? But in t, this is in time. Okay, I keep on making these little dots. Here's our phi. Here's, oh my gosh. Here's time. And what do we make of these points down here, right? These negative values in time. Well, that's a little bit weird to think about, but that's why this is weird. And we have negative and positive values in time. So these are, and we get to sort of think of these as negative and positive frequencies in time. And so we'll dive into this a little bit more, but the idea is that quantum field theory is weird. We have propagation in space, but also time, vibration in space, but also time as well. Vibration in time, again, kind of a weird thing to think about. But let's continue here and get closer to the more complete solution. So we can add waves together with higher frequencies to each other and have this still be a solution. So now we're saying, okay, omega n, we're applying n now to these things, and we're summing over n's, right? So the idea here is now, this is when n is 1, that is one particular wave. When n is 2, that's a new particular wave, 3 and 4 and so forth. As n becomes higher, their frequencies become higher, okay? And so we have this one as well, okay? But there's more to this, right? The amplitude of each wave can also be modulated, and this can also be a solution as well, because we're just changing the amplitude. Because remember, the solution is just a simple sinusoidal wave. That's not. So we can change the amplitude of the wave, that's still a solution, right? We could change the frequency, still a solution. As long as it's a wave of some sort, still a solution. So we're changing the amplitudes now. But the idea here now is that this can be a complex number, okay? So this here and these here are complex valued, okay? because phi is complex valued, we can propose a conjugated solution as well, complex conjugated solution as well, which looks like this. And for what we'll be revealing later, we're going to call this is the complex, this here is a complex conjugation, or conjugate of this. This here is a complex conjugate of this. Okay. So we're getting pretty close to a more complete solution. This actually really is the complete solution. We just need some normalization factors now. But we'll get there because we want to derive and understand these normalization factors. We are also going to need to introduce the concept of conjugate momenta, which is what we're going to do. So let's initiate this process because, again, I don't want these videos to be too long. So let's return to our Lagrangian for our spring. And when we take the derivative of the Lagrangian with respect to the temporal derivative of q, well, we get the momentum. So this here is what we're going to call our conjugate momentum, and this is how we're going to define it. So this here specifically looks like this. This is our conjugate momentum, right? So when we take the derivative of our Lagrangian with respect to a derivative of the position, right? So this is really that harkens in on that kinetic term right here. Okay, we're going to call this our position, right? So every position in space, or every point in space has a position, but it also has a momentum. Okay, and so when we know the position and when we know the momentum, we then are able to understand the complete dynamics of the system. Okay, we'll be able to predict the dynamics of the system as well. So this is our conjugate momentum. And let's stop. We're not going to quite stop here because we can take the derivative. This is just really quick, right? The derivative with respect to time, which is the momentum, right? You take the temporal momentum that gives us the velocity. Well, with respect to time, we just take the I omega out here, right? So take the derivative of this with respect to t, well, we get negative I omega. Take the derivative of this with respect to t, we get I omega. We bring this out, and so we get this. This thing is minus right here because this times this is plus, and we have the plus sign up here. All right. So this is a complex valued as well. We can also have complex conjugate for our momentum, right? So this thing we can have a momentum dagger up here, right? So that's going to be the complex conjugate of our momentum. But what does all this mean, right? So we can sort of intuitively understand what the position and the momenta of each point means, right? Because just position, momentum of each point in space and time. And we've sort of established that these things are fuzzy because they are oscillating with particular frequencies in each direction of each independent variable, x, y, and z, and t. But the conjugate momenta and the complex conjugate of the conjugate momenta and the complex conjugate of the conjugate positions are a little bit less physically intuitive. So what we're going to do is we're going to say, well, let's try to understand exactly what these are. Okay. Physically, what can we make of them? But for right now, the point that I just want to get across in the last few minutes of this video is just that we went into this continuum limit, right? Every point in space and time has these dynamics that is related to springs. Okay, springs attaching each point in space to each other. And that is, when we did that, we said our solutions looked like little vibrating points, okay? And this is really where QFT sort of clashes with GR, right? Because GR presupposes that there is a background space-time, and it's smooth, it's a manifold, and all that. QFT says, well, all these points can be described by some dynamics, and that dynamics is fuzzy, right? Because all these points are vibrating, and we model vibrations with sine waves, okay? All right, so with that being said, so here is our fuzzy positions and our fuzzy momentum. Right, okay, so what we're going to do in the next video, again, these are not totally complete yet. We need normalization factors out here, so what's more precise then is we say these are proportional. Right, these are proportional because we need normalization factors to go in here as well. So, and we'll talk about the normalization factors, why we need those. And so with that being said, make sure to hit that like and subscribe button, and I will see you guys in the next video.